Okay, so we've looked at thyristors, we've looked at why they are better in some circumstances than the transistors and better than relays. We do need to work out how to actually turn them off though, because no system wants to stay on forever. So to turn them off, we're going to take advantage of an idea called capacitor commutation. So it's a fancy word. Basically, all it's saying is for any capacitor, so let's say we've got a capacitor and there's 0 volts, it's completely discharged. If I suddenly change one of the sides of my capacitor, if I suddenly make that 6 volts, I can't instantly charge the capacitor. So this will be measuring a voltage across it, the potential difference. So this will instantly rise to the same value. And it will take time for charge to flow across the air gap between the metal plates and for it to discharge or charge. So this is the idea of capacitor commutation. This does mean if you've got a difference, so let's say you've got a capacitor where one side is 6 volts and the other is 0, it's completely charged, and I suddenly change it, and I make this one go up to 9 volts, then the other side has to instantly follow because we can't change this difference across them. If I, on the other hand, go downwards, if I make this, say, 3 volts, then the other side has to copy. So that has to go down by 6, so that can become negative. So you can get negative voltages. So we're going to make use of this to turn off our thyristors. So this is the circuit that we need to be aware of, and I'm going to talk you through the logic behind it and how it works. So in the initial state, both the switches are open. Obviously S1 is the switch we will press to turn it on, but initially it's open, and these are the switches, so they've got the whole voltage over them because they've got infinite resistance, so there's nothing going across the load. So that's 0 volts, and this is a resistor 0 volts, so this will have the whole 12 volts. So Q is at 12 volts, and P is at 12 volts. So that's the initial state. So on either side of the capacitor is 12 volts, so it's completely discharged. So that's the initial state. Okay, we now press down S1, so we close the switch, and this sends a spike of voltage and current into the gate, which turns the thyristor on. So it's like a switch we've now shut, and that means that there is 0 volts across it, which means that the whole voltage is now across the load, which means that P is now 0 volts. Now remember the idea of capacitor commutation. So before they were both 12 volts, and instantly Q has to respond and be at the same voltage. So Q is instantly put to 0 volts because the capacitor is still discharged and it takes time for it to charge. So that's immediate state after we pressed the switch. And we now immediately release the switch. The thyristor is conducting. There is still 0 volts across the thyristor, nothing has changed there. P is still 0 volts. The load has still got 12 volts. The thing that changes is Q. So Q will charge over time. So this is 12 volts, and the capacitor will be charging this way. There's no way the current can flow this way because that switch is open. So the capacitor will charge, and Q will get up to 12 volts. And so we've got 0 volts on one side and 12 volts on the other. So we have a charged capacitor. Notice the 12 volt difference. And if we don't do anything else, the thyristor will continue to conduct indefinitely, even after we've released this. And this capacitor will stay charged. Obviously, we're not going to leave it like that. We're going to press switch 2. So let's just remind ourselves where we were a second ago. So this was at 0 volts, and this was at 12 volts. And this is open, and this is conducting at 0 volts. It's 12 volts. Okay, so what happens is we now press the switch. So by pressing the switch, we've created no voltage across here because it's now closed. So we will now get 12 volts across our resistor. So Q will drop to 0 volts. But remember, we had 12 volts and 0 volts. So if Q drops to 0 volts, then P also has to drop by 12 volts. This is the idea of capacitor commutation coming in here. So P has to instantly drop to minus 12 volts. And it will have time to charge up or discharge or whatever. But in that instant, it drops to negative 12 volts. Now, the thyristor has to stop conducting because it's got a negative voltage. It's reverse biased. It can only continue conducting if this is positive. It's not. It's negative. So the thyristor turns off. And we've done it. We turned off our thyristor. Let's talk through what will now happen at P and Q as we let go of things. So we had P at negative 12 volts, Q is at 0 volts. So what will happen? So we now release S2. We now get 12 volts across this because it's an open switch. So Q will now go up to 12 volts. And this takes time, obviously, with a capacitor discharging. This has got 0 volts because it's now shut. And this is getting, 0 volts is getting 12 volts. So P will rise to 12 volts, and that takes time. And we get 0 volts across our load and 0 volts across our resistor. So we are back to the start. Both P and Q are at 12 volts, and the thyristor is not conducting. So that's capacitor commutation. I would recommend that you write down all of these states. So the initial, after you press switch 1, after you released it, after you press switch 2, and after you released it, and write down this with several diagrams. This is an exam question they like to ask for 4 marks or so. So do make sure you're really clear and you can explain all of this if this comes up in the exam. So we now know what thyristors are, what their advantages are for high power switching over the BJT or even the MOSFET. They are self-latching, so that's another advantage, and they don't wear out like relays do. And we know how to turn them off using capacitor commutation. Obviously, these won't work for AC. So the next thing that we will look at is the triac. So the next thing is triac, which allows conduction in both directions.